So for the next problem, what I've done is I've written out an integral that gives the volume of a solid of revolution and asked if we can describe the solid. The way we would describe a solid of revolution is we would give the region a description of the region that's being rotated about an axis, and we would identify the axis. So this is a little bit like the problems that we did in the case of area, where I gave you an integral and said describe the region that this integral finds the area of. Now I'm giving you an integral that gives a volume and saying describe the solid. So let's see if we can deconstruct this integral. First of all, in order to be able to say what the solid looks like, we have to be told what method it's finding the integral by, which is why I've said that it's a disk washer method. The fact is, I could interpret this integral as giving the area of a fairly complicated region. It's just that that's not how we're interpreting it. Was constructed using the disk washer method, so we're going to try to deconstruct it using the disk washer method. So the first thing we note is that knowing it's the disk washer method, we see that the integral is in the variable x, indicated by that dx there. So we know that it's being revolved around a horizontal axis. In fact, we should be able to read the axis right off the integral because we know that the axis is going to appear in one of two places. If the axis is above the region, we take the constant that gives the axis and subtract the curves. If the axis is below the region, then we take the curves and subtract whatever the constant that defines the axis is. So here we see the second case of that, or really the first one that we did in the earlier examples. You can see that -3 is being subtracted from both of these quantities that are getting squared. So we should be able to identify this as the axis, and we can write here that the axis itself is the line y equals -3. That's something we just read right off the integral. Now that we know that the axis is -3, and because it appears as the second part of the subtraction problem in each of these parentheticals, we know that the curves both lie above the axis, and the first one is going to give the outer curve, and the second one is going to give the inner curve. And really the outer curve is not always the top, but when the axis gets subtracted on this side, when we know the axis is below the region, then the outer curve is the one that's on top. So in this case, I'm going to write outer and top and inner and bottom. If you need an example where it works the other way, just remember that example where I had the line y equals 7 above the region, and the curves switched which one was inner and outer. The top one became the inner, but we don't have that here. So here the outer or top curve is going to be y equals ln x, and the bottom curve, which is just this -1, is going to be y equals -1. And what are the left and right boundaries? Well, we know that since we're integrating in the x direction, if that's the x-axis, we start with the lower limit of integration and the upper limit of integration. So we're really describing two vertical lines here, and the left boundary is therefore going to be x equals 2, and the right boundary is x equals 3. What is this? So that this is a complete description of the region. So depending on the nature of the problem, I might like you to describe it in sentences rather than just giving a list. But either way, you could translate this into a narrative description. I'm going to show you a picture of the region, and hopefully you'll recognize that this looks a little bit like a problem that we did. We have here on top, we have y equals ln x. We didn't have this part in the other problem, but we have, actually I've already written that in. And here we have x equals 2 and x equals 3. So I think depending on your class, you may have done a workshop that looked a little bit like this in the area unit, and you know that this is one of my favorite shapes because it demonstrates so many different things. So that's the region that's the region that gets rotated around an axis in this disk washer integral, and of course what we're doing is we're revolving it around the line y equals -3. So although I'm not going to mess up this drawing by drawing it as a solid, you have to imagine this region being wrapped around the line y equals -3 to form a solid with sort of a curved outside and a hole in the middle. Okay, so now we're going to do a sort of a variation on that problem. I've put up the same region that we just found in the last problem, and I've rewritten the same integral that I gave you in the last problem. So what we're now going to do is having deconstructed what that region was that was being wrapped around the line y equals -3, we're going to take that same region and set up an integral to find the volume of a solid obtained by revolving it around a different axis. In this case, the axis that we're given is x equals -2. So this is a little bit akin to those volume problems, sorry, to those area problems we did, where I said, look at this integral in the x direction. Now, draw the region and then write an integral to find the same area in the y direction. Here, what I'm doing is saying, look at an integral that gives you a solid obtained by revolving a region around one axis. Now, write an integral that gives it that gives you the volume of the solid of the same region wrapped around a different axis. And to make things a little more complicated, I'm changing the direction of the axis. Now, what does that mean? This is the line x equals 2, and it's a vertical line. So what do we know about the disk washer method? We know that when we wrap it around a vertical axis, we're going to have to do it in the y direction, which means that we're going to have to convert all of these things into y's. So recall from when you saw a version of this problem earlier that y equals ln x. This is equivalent to the curve x equals e to the y. I just get that by solving for x in terms of y. I'm also going to put in these points that we did earlier, because that'll give us some important information. Again, we did these in a previous unit. This point is 3 comma ln 3, and this point is 2 comma ln 2. And the reason that's important is that if I put in this line, this is y equals ln 2, and this line is y equals ln 3, like that. Okay, so we're going to see in a minute why those are important. What we're doing is we're revolving this region, we're revolving the pink region around this line right there, like that. So our cross sections, again, I'm not going to try to draw these to scale, but I've got, actually I was drawing inner in red, so let's do that. There's the inner part of the washer, that's the hole, and then I've got the outer part, which is going to look like that. And note, by the way, that I'm stacking this washer in the y direction. It gets thick like that, so that's why it's going to be dy. This is why anytime you have a vertical axis in the disk washer method, you have to use the y variable. There is no way to use the x variable. If you were to try to use the disk washer method to revolve a region around a vertical axis and you found yourself with any x's left in the integral, you're just wrong. Just back up and do it again, because it's never right if you would have x's in it. Again, for a vertical axis with the disk washer method. So let's figure out what these inner and outer radii are. So we can see that the inner radius is just the distance between this vertical line x equals 2 and, sorry, I should have put in here, this was x equals negative 2. So x equals 2 and x equals negative 2. So the inner vertical radius is just going to be 2 minus negative 2, which is 4. And the outer radius is going to be 3 minus negative 2, which is equal to 5. Okay, so what we can do is we can write the integral. Let's start writing the volume integral. It's going to be pi times the integral of, we have the outer radius squared. I'm actually going to write it as 2 minus negative 2 just to emphasize where the axis is. You could simplify it if you wanted to. So it's going to be the right curve minus the axis squared minus, there we go, squaring that, minus, sorry, do right minus left. So it's the right curve minus the axis squared minus the left curve minus the axis squared. And we're stacking in the dy direction. Now that goes from a low y value of y equals negative 1. I realized that in the previous example we started at 0, but this region dips below the x-axis a little bit, so the y value starts at negative 1. And then it goes up to this horizontal line, which is y equals ln 2. So I'm going to put in ln 2. But now we're not done quite, because we've only found the area up to that line y equals ln, sorry, not the area, the volume of the solid obtained by that line going up to y equals ln 2. We need to find the top part of the region, which is right up here. That gets revolved around the line x equals negative 2 as well. So I'm going to have to add another washer integral in the y direction. So this is going to be the integral. I've got this radius. I'm going to draw it again. There's the outer curve, and there's the inner curve, and there's the center. I know it doesn't look like a center, but there's the center of the hole. So I've got, what I'm going to do is the outer radius is going to be right minus the axis. So that's going to be 3. Oops. So that's going to be 3 minus negative 2 squared, just like above, because the right boundary of this solid doesn't change. Now minus, I'm going to have e to the y minus negative 2 squared. That gives me the inner radius of this solid. And finally, I put a dy, and I'm done. So is this sort of thing like a valid test problem? You bet it is.